The following video will introduce you to topography optimization using Genesis Structural Optimization for ANSYS Mechanical or GSAM. GSAM is an integrated extension that adds topology, topography, shape, freeform, sizing, and topometry optimization to the ANSYS environment. The extension provides a reliable, robust, and easy to use interface which allows designer to set up structural optimization problems, post-processing them, and export the data within the ANSYS environment. Topography optimization is a special type of shape optimization where the grids can move along the normal direction of the selected surfaces. Topography optimization is also called as a bead optimization. The creation of bead is appealing because they stiff structure with not much added mass. Stamp structures and others can benefit from this technology. Let's set up a demo problem in GSAM. In this demo, we will use an automobile hood. The objective is to minimize the strain energy to get a stiff structure. I will solve two different topography optimization problems. In the first problem, I will allow all the grids to move freely, whereas in the second problem, only a percentage of the grids will be allowed to move using bead fraction constraint. A static structural solution with two different load cases has already been set up in ANSYS Workbench. Now I will switch on the Genesis ACT extension in ANSYS. The Genesis icon will show up in the ANSYS Workbench toolbox. Now open the ANSYS Mechanical to visualize the model by double-clicking on Model cell of Load Case 2. As you can see, Genesis Structural Optimization toolbar is added in the ANSYS Mechanical with GSAM extension. Now go back to Project Schematic window. I will bring the Genesis extension into our Workbench simulation so that it shares the existing model information. Now in ANSYS Mechanical, make sure that Genesis node shows up in the project tree. Now in Analysis settings under Genesis, change the maximum optimization cycles to 50. From the Genesis optimization toolbar, push the Topography Regions button to add Topography Regions node. Design region definition is to specify the designable region for topography optimization. Only grids or surfaces will be selected as a topography designable region. Now for the geometry, select the inner side of the reinforcement shell for the hood. Perturbation is to define the type and the amount of perturbation in the location of a grid point. In topography optimization, the perturbation at a grid is almost always along the normal direction of the selected surface. For the shape type, select cone. This is to define the basic shape pattern that a perturbation controls. Enter maximum height as 25. For minimum width, enter 35. For spread, enter 10. For the edge grid design, select Skip Edge. The grids on the edge of a topography region will not be designed. It is recommended to skip edges if the designable region and non-designable region are not sharing the same grids on the edge. For design variable bounds, enter the upper bound as 0. Enter the lower bound as -1. With this selection, the perturbation will go downward. Keep the bead fraction equal to 1. The bead fraction controls the fraction of the grids in the topography region that are allowed to be moved in the final design. The bead fraction equal to 1 means that all the grids are allowed to have maximum perturbation. For bead fraction bound, select upper. This is to get an upper bound bead fraction constraint, that is, at most that many grids may move. I have already created a local coordinate system named coordinate system whose origin is conveniently located to enforce a symmetric condition. Now I will add fabrication constraints so that optimization will not lead to non-symmetric part. For constraint 1, select mirror about XZ plane. For coordinate system, select the local coordinate system. The next step is to define the objective. From Genesis Structural Optimization toolbar, push the objective button. Select strain energy as the response type. For the load case selection, select all static structural load cases. For the goal, make sure that minimization is selected. Now from the Genesis Structural Optimization toolbar, push the Shape Change Plot button. The shape change plot shows the shape change as displacements from the original shape for each grid. There are 5 options for plotting the shape change. Total, this is the total magnitude of change for a grid location. I will select the total. Optionally, the user can view the deform model simultaneously with the shape change results. Push the Show Deform Model button. For deform model, select Shape Change. Now, right-click on Genesis node in the project tree and push Solve. You can check the optimization process by clicking on Solution Information node. This will take some time, so I will skip the solve time. Scroll down to check design cycle history. The total number of design cycles are 12. At the end of design cycle 12, value of strain energy is 1.162. To view the shape change results, click on the shape change plot. Now go back to ANSYS Workbench to add another Genesis system. Drag and drop the Genesis icon on the model cell of load case 2. Open the ANSYS Mechanical and verify that another Genesis node shows up in the project tree. In Analysis Settings under second Genesis node, change the maximum optimization cycles to 50. Now copy the topography region and objective from the first Genesis system. Paste them to second Genesis system. Click on the topography regions and change the bid fraction to 0.35. That is, only 35% of all grids are allowed to have maximum perturbation. From the Genesis Structural Optimization toolbar, push the Shape Change Plot button and Show Deform Model button. For Show Deform Model, select Shape Change as Deform Model. Now right-click on Genesis node in the project tree and push Solve. This will take some time, so I will skip the solve time. Check the optimization process by clicking on Solution Information node. Scroll down to check design cycle history. The total number of design cycles are 12. At the end of design cycle 12, value of strain energy is 1.211. To view the shape change results, click on the shape change plot. Now we will compare the shape change results. In both cases, the grids are moving in downward direction, as we have entered the design upper bound as 0 and the lower bound as -1. It can be seen from the shape change results that in the case of bead fraction equal to 0.35, less number of grids are displaced as compared to no bead fraction. In the first case, strain energy is reduced by 42%, whereas in the second case, strain energy is reduced by 40%. The second case looks visually more appealing, but with the gain of 2% in the strain energy. The best structure could be obtained by changing the bead fraction in such a way that the structure should be visually appealing, at the same time it should be stiff enough. Similar example is available in step-by-step example manual. which comes with GSAM installation. This completes the demo. I hope that it has helped you to get familiar with implementation of topography optimization with bead fraction in GSAM. If you would like to learn more, I invite you to check other videos about GSAM. For more information, please visit our website at www.vrand.com or email us at gsam.support@vrand.com. Thanks for watching.